Hello, this is a review about PWM Signal. PWM signals are being used in many applications. The advantage of using a PWM signal is it reduces the heat that an electronic component might produce, as well as the power dissipation. If you eliminate the PWM signals and if you are to apply a voltage directly to a component using a potentiometer, you can pretty much do the same thing. But the disadvantage of that would be extreme heat that it might produce, as well the power dissipation. Why it produces extreme heat? Because you are applying a constant voltage to an electronic component, which it doesn't need when you're adjusting the speed or however that electronic component works. So by applying the PWM signal, you can reduce the voltage. By reducing the voltage, you are adjusting the speed or direction or whatever that you're trying to accomplish. So that is the key need of PWM signal, and that's what being used in the market nowadays. Now, what we are going to be looking at in this upcoming couple of slides, right? So we will be looking at what is PWM signal, what is signal, and stuff like that, and how does the PWM signal works, and what elements we need to consider when it comes to PWM signal, and how the calculations are being derived, like how we can adjust the signals and pulse and cycles and frequency, all those things. And some will be going through some of the examples as well. So as you're seeing here is the actual PWM signal. It's a rectangular period. It may look like a square wave at the moment, but we can adjust the wave depends on our need. Okay, so I'm just going to refer the cycles that you see below as a rectangular period signal, right? So when we talk about pulse width modulations and PWM, which is deriving to PWM signals, what we're actually looking at is either it's going to be a rectangular signal, or it could be a sine wave as well, or it could be a sawtooth, or it could be a triangular wave. But in any instances, the cycles are going to look like similar to this. So if I can go further here, it looks like a pulse that's sent every X number of 6 seconds, right? And you can also see the lower point here is the 0 voltage. If this is going to be on a graph, you can see that's going to be 5 voltage up there. It could be 5 voltage or whatever the voltage that you're producing, and then that's going to be 0. So what is actually happening here, the pulses are being given to an electronic component. Let's say 50 percentage of the time it's an on, it's at on, and then 50% of the time it's off. So that's what it's given here at. Off means 0 voltage, and then high, which is 5 voltage. So what we are looking at here is the actual pulse width and how it is being applied on a circuit, right? So as you can see, low is 0 voltage here, and then high is at 3 voltage. The period is 1 millisecond. So what its period, we will be looking into it a little deeper on upcoming slides. But for the time being, the period is going to be a combination of an off and then on. It's going to be combination of on and off signal is the period. So in here, we have 1 millisecond as the period, and the width is 50%. What is width? Is the on time or the on percentage in one cycle. We will be looking at that as well. So the rest of it is just additional stuff there. So what we are looking at here in terms of the signals, as you can see, when the signal goes up, the LED comes on. That's producing 3.3 voltage, and then when it comes down, the LED turns off. So in 1 millisecond, we have 0.5 millisecond is on, and then 0.5 millisecond, the LED is turned off. So what we are looking at is the PWM signal elements. So there are a couple of elements that we need to consider when it comes to PWM signal. What are they? Time. So what is time? Time is a period, time of one cycle. So we will be looking at each one of them. So when it comes to PWM signals, what are the components that we, or the elements that we need to look into is time, which is one cycle, pulse width. PW stands for pulse width. It's the on time in one cycle, and then D is the duty cycle, which is the percentage of on time in one cycle, and F is the frequency, number of cycles per, it says seconds, it could be second, or it could be a given number of time. It doesn't have to be 1 second. It could be the time could vary, depends on our needs. So what we are looking at here is the time. Time is period. As per the previous slide that we looked at, time is period. Time of one cycle. So what you are looking at here, the period is from the beginning of a cycle to the end of that cycle, or where the next cycle begins, right? So in this scenario here, the cycle begins here and it's the on time, and then it became off, and the off continues up until this period, and then it turns on again. So the period from the on time to the next on time is 10 milliseconds. So that's called one period or one cycle, right? So on the second example here, as you can see, the beginning of an on time, it begins here and it goes up. So that's the on time, and then it comes to turned off. At this point, the signal is turning off, and then the off is continuing up until the next beginning of an on time, right? So the period is going to be from the on time to the next on time. In this case, it's 10 millisecond, right? But what happened, even though it's 10 millisecond, there is the on time is being expanded. The on time here is lower. The on time here is a little longer. Here, the on time is even longer. Conversely, the off time is being reduced. The off time here is higher. Off time here is compared to that, it's a little, and compared to this, this is even little. But the period being still the same. Now we're going to look on the next slides what we can do to adjust the period. Can we adjust the period? Can we adjust the on time, off time? And what are the how do we call them when we adjust the signals? That's what we're going to look at. So as you can see here, so on the previous slide, we looked at a period is the combination of on time and an off time. So if you are to look at here, the period is beginning. This is where the on time starts. So one period is from this point to this point, right? In that whole one cycle, we have 8.25 nanoseconds as the on time, right? So that's the pulse width. So PW is pulse width, which is directly proportional to the on time, or pulse width is actually showing the on time in one cycle. So you have to understand pulse width is the on time in one cycle. We do not consider the off time. We only consider the on time. So in this scenario here, what we see is 8.25 nanosecond is the on time in this PWM signal that is being generated. Now, there are ways that we can calculate the pulse width. How we can calculate? If we know the DC, meaning duty cycle, which we are going to look at on the next coming slides, times time. Time is the cycle, right? One cycle is the time. So if we know the duty cycle and the time, we will be able to calculate the pulse width, right? As well, if we know the frequency, which we will be looking at again, if we know the frequency, we will be able to find the time, which is the period. And as well, we will be able to find the frequency if we know the time. Time is the cycle again. All right. So we will be doing some calculations based on these equations, but for the time being, try to understand pulse width is duty cycle times time, and time is 1 over frequency, or frequency is equal 1 over time. So on this slide here, we are looking at the D, which means duty cycle. Duty cycle, what is duty cycle? Is the percentage of on time. So on the previous slide, we looked at the on time in the metrics of time. But here, the duty cycle is actually the time, but that's calculated in percentage. We do not talk about time in duty cycles. When we refer duty cycle, the first thing that need to come into your head is the percentage of on time. So as you can see here, 50% duty cycle means 50% on time, 50% off time. As I told you earlier, one cycle is the combination of on and off. So if you consider one cycle as 100%, within that 100%, 50% time is on, 50% time is off. But we do not really consider the off time. So only think about on time, right? So that's why on the first example here, you can see 50% duty cycle, meaning 50% is the on time. So on the next example here, we have 75% on time. That means duty cycle is 75%. Here we have 25% on time. That means 25% is the duty cycle. Even though it shows the off time here, we do not take that into consideration to do any kind of calculation, except if you are given the off time, then you should be taking away the off time percentage to find the on time. So again, the calculation to find the time is 1 over frequency, or frequency. If you know the frequency, then you can calculate the time. If you know the time, then you can calculate the frequency. So on this slide, what we are looking at is the frequency. So we talked about one cycle, right? And then we talked about the duty cycle, and then pulse width. And here we are looking into frequency. So what is frequency, right? Frequency is number of cycles per period. So when you take one time, in that time, how many times the cycle repeats itself, right? So as you can see here, the first example shows 1 second. So the period is 1 second, right? In that 1 second, how many times this cycle repeats itself? It only repeats once, right? So the frequency is 1 hertz. Hertz is the metric for the frequency, right? On the second example here, it says 1 second. The period is still 1 second, but it repeats the frequency repeats how many times? 1, 2. So it repeats 2 times. That means the frequency is 2 hertz, right? On the third example, the period is still the same, but the cycle repeats itself 3 times, right? So that's why we have it at 3 hertz. So as the example shows in the top, wavelength is measured in hertz. If there one cycle per second, the frequency is 1 hertz. If there is 20 cycles per second, it is 20 hertz. 4,000 cycles is 4,000 or 4 kilohertz. All right, so we are going to look at some examples of how we can get some questions in terms of finding either frequency, duty cycle, pulse width, or stuff like that. So we're going to look at some calculations. Okay, so just to begin with, question number one here. You have a couple of numbers given to you, and then you are going to find pulse width. So in this example here, given time is 40 milliseconds. What does that really means is in one cycle is 40 milliseconds, right? And then in that one cycle, we have 75% of time is the on time, which is the duty cycle. So if you know the time and the duty cycle, how would you calculate the pulse width, right? So that's what the question is. So let me put that on the blackboard here. So what you're seeing is this is what it means, right? At the moment, what that really means is we have a graph, right? In that graph, what we have is the on time and the off time. On time, off time, on time, off time, on time. So the signal repeats itself. In here, 75% of time is the on time. Okay, this is the on time, or this can be called pulse width. And then 25% is on off time. So we're not going to consider that. Now the cycle is from the beginning of the on time to the end, to the beginning of the next on time. So this is one cycle, right? One cycle, right? Now the calculations, the question is, you know, a couple of things here. What do you know? You know the 40 millisecond is your cycle, 75% is your duty cycle, right? Which is the pulse width. So you are going to find the pulse width, right? 75% duty cycle is given. So actually, I'm sorry here, this is not actually pulse width. This is the duty cycle because you know the percentage. If it is percentage, that relates to duty cycle. And the cycle, one cycle time is given as 40 milliseconds. So the one cycle here is 40 milliseconds. So now the question is, what is the pulse width? Is the question. So we know duty cycle, which is 75%, and then we know the time, which is the period, is equal to 40 milliseconds, right? We're going to find the pulse width. So one of the equations that we looked at is pulse width is duty cycle times time, right? So if you had to put that pulse width is equal to duty cycle times time. So we know the duty cycle is 75%. That means 75 over 100 times time is 40 milliseconds. 40 milliseconds. So if you are to plug in your computer, in your calculator, you will get 0.03 seconds, which is equal to 30 milliseconds. So what that really means is the 75% of time is actually 75% of on time is equal to 30 milliseconds. And then the 25% of time would be 10 milliseconds, right? So the total is 40 milliseconds. That's called one cycle. Right? But we don't really consider this, right? The only thing that we need is the duty cycle, which is the 75%. So this is how you would find out the pulse width if you are given the other facts like the duty cycle and the time. All right, so on this example here, the given facts are the pulse width, which is 4 milliseconds, and the duty cycle is 50%, right? And question is, what is the frequency? So let's see how we can find the frequency. So what we are actually looking at on a, if I'm to put that on a graph, what we are actually looking at is this. This is the on time, off time, on time, of time, right? So the pulse width here is the 50. Sorry, the duty cycle is 50 percentage, right? That is the on time. Okay. And what are the facts that we are given? The pulse width, 4 milliseconds, right? The cycle is given as 4 milliseconds. Oh, I'm sorry, pulse width is 4 milliseconds. I'm sorry. So let me put this again. I'm sorry, I made a mistake here. Okay? So we have the graph here, 50% off time, on time, 50% on time. Okay? So in this scenario, we have the pulse width is 50%, and the time, the duty cycle, sorry, the duty cycle, I'm sorry, the duty cycle is 50%, and then the pulse width is 4 milliseconds. So the pulse width is from here to here is 4 millisecond. It's not the full cycle. Full cycle is from here to here, but we only have the pulse width, which is 4 milliseconds. So the question is frequency, right? That's the question. So we have duty cycle is equal 50%, and the pulse width is 4 milliseconds. We're going to find the frequency. Now we already know the equation for pulse width. Pulse width is equal duty cycles time, right? So we know the pulse width here is 4 millisecond, and then we know the duty cycle is 50% time. So that's what we need to find out. So that derives, we can rearrange the formula. Time is equal 4 milliseconds times 100 divided by 50. So the time is going to be 0.008 seconds, or we can say 8 milliseconds. Now the question is, what is frequency? So as you can see, frequency is equal 1 over time. So if you are to put that 1 over 0.008 seconds, you will get 125. And what is the unit for frequency? Is hertz. All right, so the next example here is we are going to find the duty cycle. So the first thing that you need to remember or remind yourself when it comes to duty cycle, it is always in percentage. So whatever the number that you're getting, you need to either convert that to percentage, meaning you have to convert that by um, depending on which side it is, you will be either multiplying it by 100 or dividing it by 100. Okay, so that's what you need, the key thing that you need to remind when it comes to duty cycle. So in this example, the given facts of pulse width is 256 microseconds, and then you have frequency as 1.25 kilohertz, right? So based on that, let's figure out what is going to be our duty cycle, right? So let me put that in here. So we have the pulse width, which is 256 microseconds, and then we have the frequency that's equal to 1.25 kilohertz, and the question is duty cycle. So to find out, you need to remind yourself with a couple of equations. What is first one is the pulse width is duty cycles times time. So if we are to find the duty cycle, we can rearrange this equation how we can rearrange this equation is pulse width divided by time is equal duty cycle. Okay. Now, in this example, we know the pulse width it's given, but we don't know the time, but we know the frequency. Now, what is time? Time is equal 1 over frequency. So if we find the time, it's a matter of applying it here to get the percentage, right? So we know the frequency is 256 microseconds. So with this, you will find the time as 0.0008 seconds. You can convert it to microseconds if you want, but I'm just going to leave it at that. Okay. Now that we know the time, what we can do, we can apply that here. So duty cycle equal to pulse width divided by time. Again, duty cycle, remember it's percentage. Okay. So if you are to put pulse width, 256 times 10 to the power of minus 6, because it's microseconds, divided by 0.0008 seconds. So if you had to do the calculation here, you will get the answer is going to be 0.32, and then you need to convert that into percentage. That's going to be 32%. So the answer here is duty cycle is 32%. So with that said, the graph is going to be something like this, right? So you will have 32% on time, and then that gives what? 68% of time, right? So 32% and 68%. So that's the question. Okay. So now you know what is, so to recap here, we looked at the periods, we looked at time, which is a period, which is one cycle, and pulse width. What is pulse width? Is the on time, and duty cycle is the percentage of on time, and frequency is the number of cycles in a given time. And then we are able to find out the pulse width. The equation for pulse width is duty cycles time time, and then for time, it is equal 1 over frequency, or frequency is equal to 1 over time. Okay, thank you.